Okay. If you can hear me, just thumbs up so I know I can start and everybody is fine hearing me. Thumbs up if you can hear me loud and clear. Okay, so are you hearing me loud and clear?
Yes, sir, I can hear you.
Okay, I'm gonna start. We'll try and squeeze as much as possible, but we don't want to give too much. If we haven't gotten to where we want, I'll ask your indulgence for another period. It's really to help you preparing for the exam. So I want to start by putting things into context, where we have come from and where we are now, before we can actually zero in onto the issue of controller design. So just allow me to wind back and take you down from where we started to where we want to be.
Sorry, sir, can you please record the class?
Sorry, come again?
Can you please record the class, sir?
I thought I'm recording and somebody stopped the recording. It is recording.
Okay, no problem. Thank you, sir.
It says it's showing recording here.
Okay, no problem, sir.
Yeah. Now remember, when we started, we had a system. And we said this system has got an input R and it has got an output Y. Now, in our space, this system, we said we can model it. A model is just, in our case, an ordinary differential equation that captures the behavior of the system. So we start off with a system, we have a model. To arrive at a model, we need to understand the physics of the problem at hand. If we don't have full knowledge of that physics, we have to do some research, consult other experts in the field until we come to a model. Now, this model ends up with a transfer function. So we end up with a transfer function, PS, in the S domain. And we have RS as our input, and we have YS as our output. All right? Now, second slide. I'm going to delete this box. So we're ending up here with a model. It's in the S domain now. And this is the system as we have it initially. Now, of course, here I'm showing one box. Obviously, from the work that we have done, you know that the system can grow into a complex network, right? Now, the next thing is what we want to understand is when we look at the behavior of this system, by behavior, I'm talking about when you excite the system with certain test input. Occasionally in control systems, it can be an impulse input, it can be a step input, it can be a ramp input, it can be a sinusoidal input or some other input, right, that we are interested in. But in most cases, we are looking at a step input. We learned that we can have a first order process and the response is just either a growing sinusoid or a decaying sinusoid. And this system here is typified by this expression, ST plus 1. And we also learned that we can have second order systems where if we have this, there are various forms of response of second order system. And here we know that the standard transfer function takes the form S squared plus 2 zeta omega S plus omega n squared. Right? Now, we say that most systems in nature are not first order, they are not second order. They may well be first order or second order, but depending on the extent to which you detail your model, you may find that the order is quite high. But we are happy to approximate most systems to either first order with delay, ST, you remember delay, time delay here, or a second order. It can also be a second order with delay, all right? Now, what happens if we find that the response of a system is not what we want, right? Perhaps it has got too much overshoot. Maybe the transient response is oscillating too much, or maybe the steady state error. You see the difference between the target and this one, that difference, ESS, is what we call the steady state error. Maybe that steady state error is too big and you want to reduce it. Now, this is what brings us to controller design. Now, in controller design, we have got a system. Again, your PS, right? We try and introduce a controller which we normally represent by CS. All right? Now, when we introduce a controller like that, this is why we also close the loop. All right? This is now this is a comparator. We close the loop through a feedback sensor, HS. And we compare the input to the output. So we generate an error here. This is your controller, CS, and this is the plant. The purpose of the controller is to try to move the process in such a way, get me clearly, the purpose of the controller is to move the process in such a way that this signal Y, when it's acted upon by the sensor, it will produce a signal that is directly related to Y. So that this error here, error is R minus Y dash. You can see that if H is 1, then this is actually Y. The Y in this character is just saying the sensor modifies the output signal. For example, if the output is temperature, normally you would have a temperature sensor here, but it will give an output which is either a voltage or a current. So that's why I'm putting that Y dash. If this output is speed, you would have a speed sensor, like a taco generator, which will give a voltage proportional to the speed. And this is, so it depends with the physical variable, which is your output. But the purpose of the controller is to make sure that as time continues, which I write as limit of E, as time continues, in other words, increases to a very big number, the error should approach 0. In other words, when you approach 0 error, you are sitting at a place where you want, because you are saying R is equals to Y dash. In other words, your system is now being driven perfectly. The input is what you are getting as an output. All right? So that is the main purpose of the controller. Naturally, systems will not attain this status without you, intervening to design a controller. All right? So it is important to understand this background to where we are. The purpose of designing C is to drive the error, which is the difference between the inputs and this output, in such a way that the error, in other words, the difference between these two, as time continues, when you are hitting the steady state, which we measure by the settling time, if you remember, settling time, all right? Then you will see that your feedback or your system is now working pretty much good, all right? Are there any questions so far to that background? Please talk, feel free to talk.
No.
Is the background clear?
No, sir.
Do you understand where we're coming from? Okay. Silence is taken to be confirmation. Let me delete this. Right. So let me go back now. I'm still laying this background to connect it with whatever we did before we actually come. Now, let's talk about tools now. A carpenter has hammers, saws, screwdrivers, and all these things, right? A welder, the person who does welding, also has tools of the trade. There's a welding machine, hacksaw, veneer calipers, and all these other things. So what does a control practitioner or a control engineer has? He also or she also has to have tools of the trade, tools to be able to model the system. We already seen the Laplace transform. We have seen the frequency domain. And we also have seen the analysis tools like the root locus. All right? The root locus is a tool. Sorry, my handwriting is, I'm using a mouse, is not the most beautiful one. Root locus. 2, we have seen the Nyquist. This is a tool which we use for analysis and design. We have seen 3, the body. There are other tools which we did not cover. For example, there's one other traditional tool which is called the Nichols chart. Very interesting and very useful. Nichols chart. We're not going to say anything about this because we did not cover it. But for what we have covered, the root locus, the Nyquist locus, the body diagram, the most commonly used tool for design is the body. And I explained why. That is not to say the first 2 are not used. They are used, right? So these are tools which we spend quite a while trying to understand how to construct them from the given transfer function and how to interpret them so that we will be able to use them. So this now brings me very quickly to where we ended, right? So now let me take a subheading, controllers. Controllers. Right. There are different types of controllers that you find in the literature, in books, and in industry. But all have got one aim, is to make the process follow the input. The input, sometimes called the reference, set point, command, whatever names, the controller is there to make sure that the output follows the input as closely as possible. Now, in the general scheme of things, there are classes of control problems. There are classes of control problems. By this, I mean, one, there is what we call regulation. Regulation. And then there is also a different type of problem, which we call tracking. As in tracking a target. All right? And then there is another problem, which is stabilization. There you know what we are talking about. You've got an unstable system and you want to stabilize it. Stabilization. So, in short, most industrial problems fall into the domain of regulation. Most industrial problems fall in this domain. They are regulation problems. Now here, what we mean is, if you imagine yourself to be an operator of a production machine, in a typical process industry, you set for long runs. For example, if you are going to produce a tissue paper, you don't set a machine to produce 2 meters or 10 meters of tissue paper, no. You can set it to produce 100,000 kilometers, all right? Or 100 kilometers. It's a long run. You see, that machine can be set and left to produce so many kilometers, maybe to run for 1 week, non-stop. So in that case, what you want is you apply a setting and you want to make sure that the setting, the output remains at that setting. In other words, the error should be 0, the input is constant. So you are regulating the output to stay at that constant input reference. The tracking can be understood if you consider what happens in the military sphere. In a tracking situation, or nowadays, if you think about a solar system, I'm sure most of us would have heard about a tracking solar system where the photovoltaic cell are not fixed at a particular angle, but they follow the position of the sun in order to maximize the incident power on the PV. So the PV moves to catch maximum amount of light. So in such a case, the tracking, the control mechanism should be able to track, follow a target whose position is changing. Another typical example for tracking is if you are a gunner, you are operating an anti-air gun, and you want to shoot at a moving target, a jet. The jet is not going to stop to wait for you to shoot it. is going to keep moving and trying to evade you, to escape you. And you need to be able to follow. So here, the setting is not like a constant, but it has to be following. So it's tracking. So you can understand the term tracking. Stabilization, of course, by implication, you have an unstable system. We all know an unstable system is one whose response is not bounded, right? You don't want that. So you can design a controller to bring the system into stability. Now, in our discussions on controllers now, we spoke about 3 types of controllers broadly, all right? I'm coming to controllers. Controllers. We spoke about the lead controller, we spoke about the leg controller, and we mentioned the PID controller, PID. So the lead, the leg, and the PID, these were dealt with fully. So I'm just going to refresh your memory very fast. The lead controller takes the form 1 plus ST. This is the transfer function now, C, plus alpha ST. And we said alpha in this case is less than 1. So this is your lead controller CS equals to that. The leg controller can take the form, if we keep alpha less than 1, it will be 1 plus alpha at the top, ST, 1 plus ST. The design parameters of both of these controllers is the value of alpha, which is a real number, and T, a time constant. Those are the 2 design parameters which we have to determine, subject, of course, to the constraint in both cases that alpha is less than 1. All right? We went through the body characteristics. You should know the type of characteristic a lead controller has and the type of characteristics in a leg controller. We discussed those. So let me not continue in terms of reviewing beyond this point. I will invite questions because now I want to focus my attention on the PID, which is the new kid on the block for now. I'm told I'll pause and I want to hear some questions, comments, anything that is not clear. Any questions, guys? Are you with me? I no longer see him tall here. Maybe he's load shedded. Non-pillow, can you see me? Can you hear me?
Yes, sir, I can hear you.
Yeah, I need some questions. Is there anything which you are not so sure you didn't understand?
No.
You want me to expand?
I'm okay for now, sir.
Yeah, okay. Pumlani? Eric?
Yes, I'm here.
Yes. Any questions, comments on what we have said so far? We're just reviewing what we did.
No, sir, I'm still good.
Okay. Who is next? Njabulo Alpha. Are you there behind the screen?
Yes, sir.
Any questions, comments?
No, sir, I'm happy for now.
Okay, can you answer this question for me, Njabulo? What is the difference between a lead and a leg controller? Ayanda? Nompilo?
Yes, sir.
You heard the question, I need the answer.
I didn't hear the question. Can you
What is
repeat?
the difference between a lead and a leg controller? Okay, let me review this because you are not giving me confidence. You said you don't have questions, but you can't answer my first simple question. All right. Guys, you need to revise, right? The lead leg. This name here, lead, comes from the fact that this provides a leading phase angle. That is the main difference. This provides a leading phase angle. All right? That's all there is to it. Provides leading phase angle. That's why it's called a lead. In other words, it's positive. A leg provides a lagging phase angle, right? If you look at the body characteristics of these two, you remember we plotted the magnitude, and we also plotted the phase angle. Same here, we plotted the magnitude, and we also plotted the phase angle. This is frequency, this is frequency, this is frequency, this is frequency. All right? Now, for the lead, the transfer functions are there. For the lead, remember, this is our transfer function. The alpha is in the bottom, right? The lead controller will do this. That's the magnitude. This is like a straight line, right? It's meant to be a straight line. And we defined this point and that point, right? According to alpha less than 1, we saw there's a corner frequency at 1/t. And then here, it's a corner frequency at 1/alpha t. There's a midpoint, all right? Whose frequency we said it's 1/t square root of alpha. right? This is where the maximum lead. If you continue down and you continue these same points here, that same points, you see that the angle curve will do this. It is a maximum at the geometric mean frequency, which is this. So the maximum, right, M max, phase advance occurs at this frequency. And we saw that that phase advance maximum is given by sine -1, right? Alpha, sorry. 1 minus alpha over 1 plus alpha. That is the maximum angle that you are going to get. Depending on your design, what is the value of alpha, what is the value of T. So the angle here is positive, and this is positive, dB is negative. The leg controller will do this like that. This is positive, this is negative. And this curve here, these points remains the same, but the curve happens on the negative side. Right? The maximum angle is still given by that. The corner frequencies are still given by this. This provides negative angle. That's why it's called a leg controller. This is called a leg controller. All right? So let's now talk about the PID controller before we run out of time. All right? Now, I know for those colleagues who are doing process, you would have seen a PID controller. I'm not going to go into details of a PID controller because of time limitation, but perhaps for the benefit of our friends coming from mechatronics, let's start by this diagram. Now, we spoke about the controller C, right? The controller C, I'm not drawing the full diagram now, the block diagram. I'm just drawing the portion where the controller has an input E, which is the error, and the output from the controller is the signal UT, which we call the actuating signal, right? So in other words, your U is simply the controller transfer function times the error, right? Like this. This is your output from the controller. Now, in a PID controller, this C can be broken down into 3 components, right? Into 3 components illustrated as shown now. So all the components receive the same signal, which is the error. So the input side, the signal is the same. So the input here, the input there, the input here is the error signal, this one. But each block gives a different output, and these outputs are added together to produce the control signal, which is U, or called the actuating signal. So we sum all these signals like that. And this output here, let's call it UP, right? This output here, let's call it U subscript I. And this output here, let's call it U subscript D. P stands for proportional. So the output is produced according to a proportional law. Let me change the color. The proportional gain here, we're calling it Kp. So the output from this, which we call the proportional part, and this is where the P comes from in the acronym PID, right? The proportional signal, UP, is equals to Kp times E. And then this second one is called integral, right? So we can write Ki in the S domain, integral is 1 over S. So this input output Ui is actually the integral of the error, which we can write as 1 over Ki. This is Ki, and then this is S E. All right. So this component is proportional to the integral of the error. This is error E. And then lastly, this one is Kd, the derivative. Derivative in the S domain is S. So UD is proportional to the derivative of the error. So it's S, K, E, E. So that the total output signal U is the sum of these three components. The component proportional to the error plus the component proportional to the integral of the error plus the component proportional to the derivative of the error. Right? That gives you the output. Now, this is what we call the PID, because the output of the controller as a whole has got three components. One component is proportional to the error of the signal of the process. The other component is proportional to the integral of the error. And the other component is proportional to the derivative of the error. All right? Now, if we go back, and we now write these equations in the S domain. We will say U, this is US, the output from the controller, right, is equals to Kp plus Ki over S plus Kd and then all this, of course, is multiplied by E, S. All right?
Ayiwo imini nginenkinga noma uChizong akasekho vele eklasini.
Hayi bo uyaphi manje Chizong? Uyaphi uChizong?
Uphumile.
Awurongo uChizong.
No, my friend, I'm still trying to open another slide. So relax.
You know what? People are just lazy to.
Ayanda.
Esibuza umbuzo manje.
Sorry, there was a fault on my side. I was disconnected. Let's continue. So I was coming from here, guys, that the PID controller, this C, we break it into 3. We produce 3 signals. One signal, which we call UP, is proportional to the error. The next signal, which we call UI, the output of that component is proportional to the integral of the error. Remember, integration in the Laplace domain is 1 over S. That's where that S is coming from. And then derivative, d dt is S, and this ud is proportional to the derivative of the error. So putting those 3 signals together, we can come to this conclusion here. All right? The output is these 3 components. Sometimes we write this as 1 Kp brackets 1 plus 1 over S Ti plus S Td Es, like that, right? Now you can see that this whole block now, this C, and this is our P, it receives E and produces U, the control signal. The transfer function in this case is simply U over E is simply Kp 1 plus 1 over S Ti plus S TD like this. Now, of course, it's not difficult. It's just a matter of maths, right? You might ask, what is the relationship between TD and KD? Here we had KD. If you bring this KP inside the bracket, then if you take this one term, according to this formulation, this S term is going to be S times TD times KP. So in other words, S TD times KP is equals to KD, all right? S, meaning that our KD is the product, right? Sorry, yeah, this is the product TD times KP. Or you can write your KP as KD divided by TD, right? So TD times our original KP is equals to KD. You are just equating coefficients of like S terms. So you can interchange your expression either in this form or in that form, right? So this is what we call the PID controller. It has got 3 components. But why having those 3 components? Right? I'm winding to a close now. I don't want to take you a lot of your night. I have other things also here. Right? Very quickly, why PID? Why do you use it? 90% or more of the controllers that you find in the process or generally in industry are of this type, the PID controller. Am I still recording? Yes. Right? They are of the PID type. The KP is used to increase the speed of response. Speed of response. It increases the bandwidth. If you are talking in frequency terms, increases omega BW. I'm writing in a short way, the system bandwidth. The P controller also has a property of reducing the steady-state error. Steady-state error. But these are the advantages. It has disadvantages, right? The disadvantages can outweigh the benefits depending how you set the value of K. If you remember from the root locus, if you take a simple problem that we have seen, we are familiar with a root locus like this. Please remember the root locus doesn't have to be this all the time. You should follow the rules, right? Sometimes a root locus can be anything. It can be like this, right? You have to follow what the rules are telling you. Don't just stay, oh, because it was like this in class, so it will ever be like that. No, that's wrong. Follow the rules. Now, at this point, we call the critical gain. If you increase this gain beyond this point, remember this is the right half plane, which is unstable, and this is the left half plane, which is stable. So if you keep increasing this gain, you may actually find that your closed loop roots, they move until they become imaginary, in which case you start the process oscillating. Any further increase in gain, you are now hitting the right half plane and your system becomes unstable. So too much gain can lead to instability of the system. Instability, it should be L. Instability of the system. Now, those of you who actually did the simulation, you will see that as you increase the K, the system's oscillations were also increasing and the overshoot was also increasing. The settling time was also increasing. So all those things are disadvantages. They are not advantages. So the transient response can suffer, meaning you have too much and oscillations before the system settles. In a real process, that is always very undesirable. It can lead to a lot of rejects or loss of material and such like. A production manager will not allow you to do that. All right? Now, so much for the P control. What about the I components? The integral, I. This is the integral. Components. All right? Question 4 in the exam is talking about all these things, guys. The integral component, all right, in the system. All right? So, what you are going to experience with the integral portion of the controller is that, one, you can eliminate steady-state error. Steady-state error we already illustrated. Right? If this is your time and this is your output and this is your input, if your first order system is doing this, this gap here is your steady-state error. If your gain is very low, you may find that your process will be slow like this, meaning that the gain is low and the steady-state error will be high. Right? If you put a PID in a process, you may find that it is able to eliminate the steady-state error. You know, I meant to draw this to coincide with that signal here. Let me give it a new try. This is my input. I'll just try to draw them like that. Yeah. You see, if you do I control, it can eliminate steady-state error. But one big disadvantage of integral control, it can also lead to instability. instability due to the minus 90 degrees phase lag it introduces. To the process. The benefits can eliminate the steady-state error. Big disadvantage can cause a system to go unstable because of the minus 180. Remember, it's this 1 over S. The angle of this term is a constant minus 190 degrees. All right? Now, what about the D term, the derivative term? Now, the D term derivative term is well known sometimes as velocity feedback. Remember, velocity d dt, the rate of change of something. This is equivalent to s in the Laplace domain. When you find if this is distance x, then dx dt is speed, which is s. That's why if it's temperature, still it talks about the speed of rise of the temperature. All right? If it's mass, dm dt, it still talks about speed. Is the rate of change of the mass. So that's why this is called velocity feedback. The main benefit of velocity feedback is that it increases system damping. One increases, this is C, increases damping. This is meant to be A. Increases damping. All right? That is the main benefit of velocity feedback. So if you find that the process you are dealing with has got low damping. Low damping, it means when you look, say, if it's a second order system and you put a step response, it might be responding with a lot of oscillations like that in the long time constant. If you put, depending on how much you put of the velocity feedback, you may find that it is going to change and do this. Right? So you are able to increase the damping and better the transient response. One well-known disadvantage of velocity feedback or derivative control is noise amplification. Noise amplification. Derivative feedback has the potential to worsen the effect of noise on the output of a system. That's what we mean, because remember, any process, there's always some background noise input to it. Derivative has got the undesirable effect of accentuating, or in other words, increasing the effects of noise. So overall, you don't want noise to be increased. So now, how do you make sure that when using these three the three-term controller, the PID controller, right? How are you going to make sure that you can reap the benefits but avoid the disadvantages, right? Now, this problem is called tuning. Tuning a PID controller. Tuning means setting the values of KP, TI, and TD. What values are you going to have, right, in order to make sure that your process behaves in a desirable way? That is what we call tuning, like tuning a guitar, right? How do you select the values of these three terms of the PID controller, right? So when we say the three-term controller, we're talking about the three parameters, KP, TI, TD. Or you can say KP, KI, depending on the
Yes.
formulation, KD. Yes? Right? So there are predominantly two traditional methods that are used to select these values. There is what is called Ziegler. Ziegler is the name of the person who devised it. Ziegler-Nichols. These two gentlemen devised two methods. One is called the reaction curve method. And B is called ultimate cycle method. Ultimate cycle method. So those are the two methods which these two guys devised, right? I'm going to talk to one method, right? And come to a stop for now. I've not been able to finish whatever I wanted to say, but I've said most of it. So let me repeat myself. The PID has got three parameters which need to be tuned or whose values need to be set. Are you going to put KP equals to 10? Are you going to make TI 0.1? Are you going to make TD 0 or whatever the value? Now, if you don't have some routine or a technique to set these values, of course, there are a million ways of selecting these three values. So how do you know which one is the best? That is what we call tuning. And I've said here there are two methods, traditional methods, the reaction curve method and the ultimate cycle method. I will describe the ultimate cycle method and close. Right. The ultimate cycle method is also called the closed loop method. So let's redraw our closed loop. This is our plant, and this is our controller. See, and they are connected as usual. Like this, there you have your input, positive, and there you have your feedback coming like that, and you have your H, the feedback sensor, and there you've got your output like this. This is a closed loop system, we know that, right? and the error is here. So, and this controller for our sake is a PID controller. That's a PID controller. So we know there are three terms, KP, TI, and TD, that need to be tuned. In other words, the value set. What this method says is as follows. First of all, set. You remember the simulation practical? Set TI equals to 0. Set TD equals to 0. That's the first step. Then you run the process to run the process with KP being increased gradually. I'm showing my increase like this. So you are increasing the value of KP gradually. Remember, in the simulation, I said increase KP and observe what's happening. Right? Of course, if you've done your work correctly, you'll see that this is a third order system that you are dealing with. Add some value of KP, which corresponds to the critical point on the Nyquist, on the root locus, this point here. You'll see that the system breaks into continuous oscillations. You get a sinusoidal response at some point of KP. The corresponding value of gain is what we call KU, the ultimate gain. The name ultimate cycle, this is called the ultimate gain. So the method says that when you have reached this status where the system's response now is a continuous sinusoid, in other words, you have attained the ultimate gain, you should note the value of the ultimate gain, KU. You should also note the period, right, of those continuous oscillations, which is now Y. This is your response Y. You should also note TU, which is called the ultimate period. So let me repeat. You run your process in closed loop. You set the integral time constant, Ti equals to 0. You set the derivative time constant, this parameter Td, equals to 0. Then you run the process. At each stage, you increase Kp, the gain, and observe the output. You keep increasing the gain until at some point, the response breaks into continuous oscillations like this. It will give you bounded response, right? Not an unstable response. It will be a bounded continuous oscillation. When that happens, you stop increasing the gain. You record that value. That is what we call the ultimate period, K subscript U. And you record the, the ultimate gain, K, and the period, right? With instrumentation available today, you would have hooked some computers. So this is just a matter of reading. If you are using an oscilloscope, you know how to measure that period and things like that, right? So when you have done this, the last slide, gentlemen, so last slide, I'll just need to show you this. Just help me, let me, there's something I want to find here. Yes. Something. Okay. Not coming out nicely. Let me try again. So picture. Bear with me. I'm copying something I want to show you from somewhere. Maybe somewhere. Okay. Right. I'm sure you can all see the table that I have. All right. Now, the Ziegler-Nichols ultimate cycle or closed loop method comes with a table like this. Now here, I'm just showing one entry, but the full table will be maybe something like this. Come on. We want to close now and it's misbehaving. It will be something like this. Right. So here it will have P, and then you can have PI, and then you can have PID. So I'm just showing you this part here, which is corresponding to the last row. There is PI, which is missing in this table, right? And then at the top, you are going to have, of course, KP, TI, and TD. What this table is saying is that you would have run this experiment and you would have measured the ultimate period. If it's in a test or in an exam, the ultimate gain and ultimate period is these points which you find on the root locus or using the Routh array. You see, using the Routh array, you can find TU. Only remember that the relationship between time and period, 2 pi f is equals to omega, all right? And f is equals to 1 over period. So you can substitute for 1/t here to get your TU, all right? So suppose we have found that KU in our experiment is equals to 10. And we have also found that the ultimate period is equals to 0.5 time units, seconds, minutes, whatever. So the ultimate method says now you are going to set the values of K in your PID controller. All right? Meaning that all the three components of the controller are active. So it says set the value of the proportional gain to 0.6 times the ultimate gain. So here the ultimate gain is 10 times 0.6, which means you must set this to a value of 6. The integral time constant Ti says set it to half the value of the ultimate period. You measured and found that the ultimate period is 0.5, which means this you must set to 0.25. And lastly, it says the TD, set it to TU, which is 0.5 divided by 8. So it will be 0.5 divided by 8. It will be 0.0 whatever 625. So these are the values that you come back and put here. All right. So your KP now is 6. Your KI, whatever value from there, your TD, KD, whatever value from there, right? Or if you want to express it in terms of the T's, you would come back to this equation here. Now you have found the value of KP, set it to 6. So this will no longer be KP, it will be 6. This TI will be 0.25 or whatever the value down there, and then this TD accordingly. And when you do that, you would have said you have tuned your controller. Now, P is when you are using only your P controller, meaning I and D are 0. All right? That's called the proportional controller only. PI is when D is 0. You are not using the derivative portion. You are only using these two. And here you are using everything. Guys, I think we will stop here. I will speak to Nto. Sorry for taking your evening, but these things are important. Time has been a difficult commodity for us this semester. Are there any questions?
Yes, sir. Can you
Yeah.
kindly repeat the last part? I didn't hear you well, the PID part,
Okay.
the calculation.
The calculation. The
Yes.
calculation. Okay. Okay. I'll put a new slide. You see, what we are using is what we call the Ziegler-Nichols ultimate cycle method. Now, these are small equations which this gentleman called Ziegler-Nichols devised to help us to set the value in a PID controller, KPTI-TD. If I just give you a PID controller and say use it, you see these three parameters here, KP, this is your K, TI, and TD need to have values. You see, they need to have specific values. So what we are saying is, if you are going to use, this is what we call the closed loop method or the ultimate cycle method of Ziegler. It tells you here that in your process, you need to tune TI, TD, and set them to 0. Then you increase the gain in steps until your process response becomes a continuous oscillation. In other words, a sinusoid, pure sinusoid. When it's like that, you now need to measure that value of gain where the oscillations happened, and we are calling that value Ku. And in the example I gave, I said, let's say that value you measured it and it was 10. And you need to measure the period of the sinusoidal output, right? And I said, in our case, let's say that period, we've measured it for the process and it happens to be 0.5. Now I have to decide what should I set value of Kp to, right? What should Kp be? And what should Ti be? And what should be Td? If I am doing this, I'm using the full term controller, which means my controller have got all the three parts, the proportional, integral, and derivative component. So I now go back to these little equations. According to this method, I must set Kp to be 0.6 of the ultimate gain. So I say 0.6 times 10. Because 10 is what I measured to be the ultimate gain. So this gives me a proportional value of 6. This one, the derivative, according to this, it says set it to Tu divided by 2. But Tu is 0.5, so it's 0.5 divided by 2, which is 0.25. In other words, in my PID controller, the Ti must be set to a value of 0.25. And then Td, I must set it to Tu divided by 8, which means 0.5 divided by 8. And this is what I get as 0.0625, whatever the number. So this becomes the value of Td. You see that? So now if I go back to my PID controller now, which is this equation, this one. In here, the value of Ti should be this value, 0.25. And the value of Td should be this value. Right? That's this value. And the value of Kp should be 6. When we have done that, we say we have tuned the PID controller. Right? Then the other thing which I mentioned when I went back to this table, I said this example here, I'm only showing you in the case where we are using the full PID controller. Now, sometimes we don't use the full 3 terms. We use P, in which case our controller will just say it's a proportional controller. I and D will be set to 0. Sometimes we use PI only, which means the D part is not present, in which case we just call it a PI controller. Or if we are using all, as we have done here, it's just a full PID controller. Now, for P and PI, there will be similar equations here, similar to this, right? There will be similar equations. Sorry, because this is P. You won't have anything here. There will only be an equation here. You see? For PI, there will be an equation here and nothing there because you are not setting Ti. Remember, this is Ti and this is T, this is Ti, this is Td. If you are using a 2-term controller, this one does not come into the picture, so it's not there, right? You will have some equations here similar to this, but I'm not saying here, if I remember well, right? The file is refusing to open where I've got this table. Maybe it's in a different hard drive. It might be 0.5 Ku as an example, you see? So it is saying set the proportional gain to half of the ultimate gain, just like that. In which case you calculate 0.5 times 10, it will be 5, and you are done. You see, there will be another equation, and you substitute those values, and you determine those values. Then you take them back to the controller, and your controller. Remember, if you were simulating, I said now simulate with a PID controller. You would need specific values for these parameters. You see, when you didn't know these methods, some of you were throwing just any values. And I came around, I said, no, set them to 0. You see, because I knew, but now we all know that is what was happening. You see. I don't know if that helps.
Yes, thank you.
Guys, we'll call it quits. I'll speak to him too. You can see that we tried to do a lot of things here, and we certainly could not touch the revision of the test. This is important, all right? So good night, and I'm trying to put your marks on ITS. I've marked quite a lot of the practicals. Some of them were disappointment because some people will not be being honest. But if we didn't have this, my hope was to actually have logged in all the marks now. You have seen them. The only mark which you haven't seen is the prac mark. So I'm busy trying to finish that. And then when I have all the 4 sets, quickly I'm going to load them. I'm sure over this weekend, you should keep checking. You will have all your marks. And then I will compute, hopefully Monday morning. Thank you. Good night. Bye.